mostly on projects which have used Oracle at the back end. Presentation. So I hope you find it useful. Can I just get a show of hands? How many people have used kind of relational databases before? Oracle, Postgres, MySQL. Okay, that's great. And how about graph databases? Anyone had some exposure to graph? And Neo4j, anyone? Okay, great. Just a couple of people. That's great. Okay, so just to get an overview of what I'm going to talk about, first of all, I'll give a comparison from a data model perspective between the graph and the relational database. I think that's kind of the key driver of why you'd use a graph rather than a relational database. I'll talk about the domain that I came up with for the blog post, which was the Bath Christmas Market, and a use case similar to the kind of travelling salesman problem. I'll then give an intro to Neo4j database, the desktop, the developer tooling that they offer, and a kind of a brief introduction to Cypher, which is the query language that's used by Neo4j. And then we'll have a look at solving a travelling salesman type problem with Cypher. Okay. All right, so start off with a comparison between the two. So the top picture may represent how data is stored in a relational database. The green block on the side would be records in a person table. So you've got Alice there with an ID of 815. The yellow blocks on the right, those might be a department table. So 3 records, 111, 119, 181. And then in the middle, we've got the many-to-many table, the purple table, which links a person to multiple departments, and a department can have multiple people. So how would we go about querying, for example, getting all the names of people in the IT department? Well, it's quite a straightforward query. First of all, perhaps we'd use an index lookup to look at the department table to get the ID of the IT department. So we'd then again, maybe use another index to find all the IDs in the many-to-many table for people who are in the IT department, and then we'd use another index, probably the primary key, to have a look at the person table to find the names of all people. And so we're essentially using 3 indexes there, 3 lookups. In the graph database, in terms of nodes and relationships, so nodes are instances of data. There would be a node for Alice with the label person. So nodes are labeled with one or more labels. We'd have a set of department labels. There's 3 there. There'd be an IT department label. And then you've got relationships, which are references, effectively, of the instance nodes. So node, there'd be 3 references to 3 different departments in the picture. And actually, there'd be a reference on the departments too, pointing back to Alice. Look at lookups for the relationships. If you wanted to do the query, you'd first match for the department, the IT department. That would perhaps use an index, but then as soon as you've got those departments, you've got direct references to the people in it. So instead of having 3 index lookups, you've got effectively 1 index lookup. So if you've got a lot of data in your system, you can see why it might be more efficient to use a graph database for certain types of problem. Okay. So this is kind of the domain and the use case that I wanted to talk about and what I came up with in the blog post. So it's based on the Bath Christmas Market. You can see At the top there, Milsom Street, a set of purple chalets. You've got some green, some red chalets there for Bath Street. You've got a whole load of other chalets around the Abbey in different zones. So it probably is a bit early to talk about Christmas, I think, and I am a bit kind of long in the tooth, middle-aged, a bit grumpy. So what I found with it though was that the pictures in the on the website for the Christmas market, you see a lot of people full of wonder, full of awe, but the reality of the Christmas market when you go on there, it's a logjam of people. So kind of that gave me the inspiration for the use case, which was to say, okay, what I want to do is select a few chalets, select for where I want to get presents, and then find my way around the market as quickly as possible, as efficiently as possible, by visiting each of those chalets. So that's got its similarities with the travelling salesman's problem, where with the travelling salesman problem, you have a salesman who visits a whole load of cities, and the idea is they've got to visit the cities as efficiently as possible around the map. So the difference is, though, I mean, you've got with the travelling salesman, you're typically talking lots of cities, and you can't solve that kind of problem deterministically or with a brute force algorithm. With this, I've only got 60 chalets, so I'm looking at solving it with a kind of a brute force algorithm. So I'll get that out up front. Okay, so let's have a look at the data first of all. All right, so this is how I'm modeling the data. So essentially this first spreadsheet is the set of chalets. So there's about 60 chalets in there. Each one has got a number, a name, a description, a category, and the zone that it's in. And then on this other worksheet, we've got a set of links where I've costed links between two chalets. So the idea is that you cost a link between certain sets of chalets, and then to find that route around the market, what you want to do is to minimize that cost as much as possible. The minimum cost should be the quickest route. Okay, so let's have a look at the Neo4j tooling. So you get a place to put your projects, and then here on the right, you've got these kind of three areas. You've got the database there in the middle. I've called it graph. You can have multiple databases. At the top, you've got a set of applications. So the Neo4j application, the graph app Neo4j, is effectively very similar to SQL Developer or Toad, or one of those tools that you use to query SQL. It will let you write the query and it will display the results. And then on that bottom row, you've got libraries. So effectively, they're like store procedure libraries, if you're thinking in Oracle or Postgres. So you've got an APOC library, which contains a load of graph utilities. And then you've got a graph algorithm library, which lets you run lots of different algorithms, shortest path, similarity algorithms, that kind of thing. And you can add more applications. There's about 7 or 8. So there's applications for things like being able to do ETL, to transfer data from Oracle into Neo4j. You've got database monitoring tools. It's kind of growing all the time at the moment. They seem to be. I think Neo4j has just got some new funding, and they're really kind of boosting their product at the moment. Okay, so let's have a look at the Neo4j Browser and get a feel for that. I think maybe before I go into that, it's kind of maybe useful to think about when's the right time to use Neo4j rather than a graph database, rather than an Oracle database. And I've kind of got my perspective on it. People give different answers, but my feel on it is when there's lots of many-to-many relationships in the database, that would be a kind of a good indicator. When the connections in the database are as important as the elements themselves. So thinking about things like similarity algorithms, where you've got users and you want to make recommendations to those users based on how those users are connected to other users. So in that case, it's very important to understand the connections. So that's another kind of indicator to use Neo4j. I think for things like route finding, I think there's definitely use cases there, and maybe hierarchy traversals. You can, if everyone's worked with hierarchies in, say, Oracle, they can be quite slow, those queries, and having these direct references to connections tends to can provide use. But I think typically when you've got lots of data, if you've got queries that aren't performing and you've tried optimizing them, then you kind of maybe thinking about graph at that point is a good idea. Okay, so here's the Neo4j browser. So I've got a load of save scripts here. It comes with some sample ones out of the box. If I open these up, so I think the first thing we want to do is load up the data. So can everyone kind of just about see that, or do I can make it a bit bigger? A bit bigger, okay. How's that? Is that a bit better? Yeah. Just about? Okay. All right, so this is Cypher, the query language, and you can kind of see similarities with SQL. The create statement, the merge statements are both similar. It does have the facility to be able to load data from CSV files. So the first thing we're going to do is load up the chalets from that chalet worksheet. And essentially what it's doing here, it's locating the file in the system, and then it's creating for each one of each record in the file, it's creating a chalet node with the properties number, name, description, category, and zone. It's also creating a zone node with the property name, the zone name, and it's also creating a relationship which is the zone hosts the chalet. So it's doing three things. We'll just run this. There's around about 60 nodes. So it's creating 60 chalets, and it's creating eight zones, and then relationships. Each zone hosts a chalet, so that's why we've got 60 relationships. Right, we'll have a look. We'll load the links up too. Okay, so with the links, again, something very similar. What we're doing now is we're matching, which is similar to a select statement. We're matching chalet nodes in the database, and we're matching that with the from column from the spreadsheet to gain the chalets. And then once when we've got the chalets, we're creating a links to relationship between each of the chalets. Okay. So we can now visualize the schema. This is a built-in. Once you've created the data, it doesn't work like relational databases where you create the metadata up front. You would normally define the tables you want and the columns the tables and the columns up front. With Neo4j, what it does is you create instance data. So this schema visualization is based on that instance data. It's effectively deriving the metadata based on the instance data. So we run this, we can kind of get a flavor of what it looks like. So this is using d3.js is built into this to be able to draw these graphs. So you get all the niceties with D3. You can move it around, you can zoom in, etc. You can blow this up like that. Now, what we've got here with the tool is you can click on these labels at the top. So we click on the chalet, for example, and I can say name, and it will put that there, put the name there, and we can click on this here. We can do that with the links as well. We can say type. So now we can see this is our model, effectively. We've got a zone, it hosts chalets, and chalets link to other chalets. Quite straightforward. Okay. Right, so let's have a look at a few other queries, what else we can do. So this is how to show chalets in tabular form. So essentially we're matching the chalet, which is a node, and then we're returning properties of that node. And we're doing an order by clause. Again, very, very similar to SQL, and quite familiar. So if we run that, you can see, here we go, we've got a table of the data, which looks pretty much like what it looked like in the spreadsheet. So far, so good. Right, what we can also do is we can use that little visualization tool to be able to display the data as well. So if your query returns either nodes or paths, then it will draw those nodes or draw those paths as part of the visualization tool. So in this case, we're just matching the chalet and then we're returning each node. So what we'll see here is again a load of all the chalets but drawn as nodes. And what we can do, it's got nice little tools. You can kind of drill out like that, and you can click on that and you can explore the data a little bit more if you want to. It's quite nice little tool. Okay, so let's kind of build up the query a little bit more. So this query is about showing the links between, oops, sorry, let's show this one first. Yeah, no, this is the one. Okay, so let's show this one. So this query will show each of the zones and then all of the chalets that are in that zone. We run that. We're kind of being able to build up a picture of the data now. Okay, so we've got Bath Street. Here are the chalets that are in Bath Street. Here are the chalets in York Street, and so on. So what we haven't got yet is the links between zones, chalets between zones. This is just within zones. In fact, we don't even have the links within the zones at the moment, but we've got another query for that. So I'll run this one. This query is about showing what we've just shown, but also the links between each of the chalets within the zone. So again, we've got two paths here now. We've got the first path. We could use a where clause, but I've chosen to do this with two paths. The first path is showing the links between chalets, path P, so that's C1 links to C2. The second part of the query, the second path, is showing a zone that hosts both C1 and C2. So that's not going to show the links between zones, but it should show the zone, the chalets in the zone, and the links between those chalets. So we pick this one, for example. There we go. That's quite nice. So we can see what's going on there. Okay. Okay, so that's quite pleasant. Again, we're getting a better picture of the data. We made the query a little bit more complicated. Now let's just show a few more things that we can do with it. So what would be nice is at the moment all those chalets are being shown the same colour. They're all being shown in orange. What would be nice perhaps would be to colour them in by zone, which you can do with the tool by having different labels on the chalets. So if we add zone labels to each of the chalets, we can, like this. So the way that this works is that again, you're matching the chalets. You're using the node itself and the zone property on the chalet, and then calling this APOC function, which allows you to add labels to each of to the given node, and the property that's passed in is the zone property, and this will return the nodes. So if we run this, we're adding additional labels. So there we go. We've coloured in the nodes, and now if we run this link between chalets in zones again, we've got a nicer diagram. Different zones should have different colours. Let me just blow this up so I show this a bit clearly. There we go. So we've just improved the visualization a little bit. Right, okay, so that's kind of our introduction to Cypher. I'll show one more thing, which is the links between all chalets, so it's a little bit, and I'll make this a little bit smaller. Oops, that's not going to do it. Okay, here. Okay, so that's the whole graph. So not every chalet is linked. Chalets next to each other tend to be linked, and chalets that are close to chalets in other zones, they're linked. Not everything has a cost, but it's kind of that's the kind of graph going on. Okay, so let's start having a look through the algorithm now. So now what we want to do is to be able to travel through the market as efficiently as possible. So I've broken this algorithm into kind of three steps, and I'm solving it deterministically, as I said before. I'm not using some AI technique to do it, but it'll be interesting to see how quickly it can process the data, because there's still quite a number of combinations. Before I do that, actually, I do need to do this. So before I do this, I'm going to select some GIFs. So these are the chalets that I've chosen to get GIFs from. So I pre-selected that set of data. And all I'm doing here is saying, it's quite nice, you can pass in a list, and then that unwind function will convert that list into rows of data. I'm then matching up the chalets, and again I'm adding a selected label, and I'll use selected labels later to be able to reference the GIFs. So I'll just run this to select the GIFs. I've got some sausages for Grandpa, some stuff for the dog, chocolates for the wife, so it's all good. Okay, so let's have a look at the algorithm now. Now we've selected the GIF. This first step in the algorithm is going to essentially create a mesh. It's going to look at each one of those selected chalets, and it's going to find the shortest distance, the shortest route between that chalet and another selected chalet. So it's going to build a mesh of data where each of the selected chalets connects to each one of the other selected chalets, and on that mesh, on that link, it's going to put a cost, the total cost of getting there, and it's going to use the interim chalets that it used to get there. So that's what this first step is going to do. So essentially, the number of combinations you're talking there is there are eight selected chalets. So you're talking 56 combinations, which you can halve to 28, because if it's the cost in one direction, it's going to be the same as the cost in the other direction. So that's what this query is effectively going to do. So it's looking at the chalets. So it's getting one set of chalets and calling it C1, and it's getting another set of chalets, selected chalets. It's getting another set of selected chalets where the chalet number is greater. So that's the way of kind of just getting half of them, not so that they don't join to each other, and that they don't that the return route isn't taken into account. It's then using an algorithm from the graph library, algo shortest path, to on the links to relationship. It's using the cost, and that algorithm is the one that's going to return the total cost and the nodes that it used to get there. So this is just some, this with statement here will then collect it all up. So you've got the cost, you've got the shortest hop nodes in between, and then it's creating a new relationship between each one of the chalets, this shortest route to here. It's creating a new relationship between each of the chalets, which is called the shortest route, and it's putting some properties on that relationship, which is the total cost and the collection of hops that it used to get there. So if we run that, so that runs pretty quickly. To do that calculation, it's doing that pretty quickly behind the scenes. And we can view what it's created. So we can view this mesh of shortest path. Okay, so what I need to do here, let's change that. There we go. Okay, so that's that mesh, and I'm not sure if you can quite see it, but it's essentially, it's got the cost on there. It's got the cost between each path. Okay, so that's the first step of the algorithm. The second step, so what we want to do with the second step is now we've got our mesh of potential routes, and what we want to do is find every single route in that mesh and order it by the total cost and take the one off the top, and that's the cheapest. Okay, so that cheapest route will give us that will give us the most efficient route through the market, hopefully. And again, there's a procedure to be able to do that. This APOC path expand config. So what we're passing in here, we're saying we want to use the shortest route to link, which was the one we just created in step 1. And we're saying we want to traverse 7 levels. So we've got 8 nodes, so we want to hop 7 levels, and each one of the nodes in that level has to be unique. So that should return every single potential route based on that route mesh. So we get the data, we can extract out the chalet numbers we want to see returned. We want the total cost of the routes, so we can use an inline reduce function to be able to do that. And we want to extract out the interim hops as well, so that we've kind of got a route through. And then order by the total cost, limit 1 will just return the first record. Okay. Okay, so there we go. That's return that, and you can see that was very, very quick. That was 628 milliseconds, and that was evaluating 8 factorial routes. So that's 40,000 routes, and you could have put an efficiency again just to make it half that. But actually, that's pretty quick. I'm not sure. I haven't tried that in Oracle, but that feels pretty quick to me. Under a second for 40,000 potential routes. I think it's the correct answer, but we're not going to look at that. So, okay, so what we can see here now is we've got the ordered chalet numbers and the total cost, and here we've got, I'm not sure if you can quite see those, I'll make them a little bit bigger. Okay, so each one of these, so we've got an array of arrays, and each one of the inner arrays is a segment between the chalet numbers. So we're saying we want to visit 8 first, then 14, then 59, and so on. And then the first segment is 8:13 to 14, so it starts at 8 and it ends at 14. That sounds right. And then the next one starts at 14 and it goes to 59. But looking down a bit further, there's one there that starts at 42 and ends at 43. So that segment's kind of the wrong way around. It's the correct data, but because of the way that the data's modeled and because of the way it found the shortest path, it's showing it in the wrong order. So it just needs to be turned, that segment. So that's step 3, really. So that's it's quite straightforward to do that. You can have a case statement inside your cipher. So essentially what we're saying is we're going to look through each of the selected chalet numbers. So we know it has to go at 8 and we know it has to go at 14. So we know segment 1 has to start at 8 and 14. So the case statement is just comparing the first item in the inner list to what's the chalet number, and if they're the same, that's fine, and if they're not the same, it's just going to reverse the segment and return the data. Okay, so there we go. That's saying the route through the market. So that's good. That's kind of solved the problem. There is one more slide I just wanted to show, or one more query. So what I wanted to do was kind of using the nice visualization that's available in the tool. I wanted to kind of show a visualization of that route, so that to finish off. And one of the nice things you can do is you can create virtual nodes and virtual relationships in line in the query, and essentially because the because the tool can display virtual nodes and relationships. If you can create these nodes and relationships, you can use those to kind of display whatever graph you want. And then the APOC tool itself is the one that creates those. So that's what this query is doing essentially. It's creating a load of virtual nodes and virtual relationships so that I can display the route. Okay, and here it is. I'll just tidy it up with this. So we've got title here. I'll do that on chalet too. Okay, so this is kind of the route through the market. So we can start here. This is the entry point, and we go to get the sausages first from Milsom Street, and then we move into Bath Street. These slightly bigger circles are the selected chalets. The smaller ones are kind of interim ones. And then we wander through Bath Street, and then we move here into Abbeygate Street, all the way around here, and eventually we come out here. These arrows are reversed, so they're shown next. So what's going on here is you're coming down here to the chalet, you're coming back out, and then you're going along here to the exit. That's all I have. Any questions I can answer?
Repeat the question for the recording.
Yes, yes. Yes.
So you picked 8.
Yes.
To search for.
Yes.
Presumably, because if you picked 12, it
Yeah.
would have taken longer than that.
That's right. Yeah. Yeah. Yes. Yeah.
Are you, with those constraints on these built-in or these available brute force algorithms,
Yeah.
are you aware of anyone who's using those kind of brute force path enumerations in the wild?
No, not for this kind of problem. I mean, I don't think it scales. I'll be honest about that straight up. I kind of picked this problem because I wanted to play around with the graph database, and rather than because I wanted to solve the problem using the graph database. I think though, to be fair, I think Neo4j do kind of more recently, they have, like I said, they've been kind of gaining traction recently. They've got a lot more seed funding, it seems, so they're kind of improving their product, and they have kind of put more of a bent on machine learning and AI techniques. And I mean, it is a graph problem, the travelling salesman. So it kind of makes sense to model it as a graph structure and then provide the algorithms on top. But this algorithm wouldn't cut it for kind of a travelling salesman. 8 worked, and I thought, okay, that'll do. That's nice. Okay, any other questions? Yes.
Like, what I understand, chalets are the different areas, and which is each of them having zones, and they are connected to each other by some network paths. Is my understanding correct?
So the question was about the model itself and what the model looks like. Yeah. So the model is there are zones which are models as nodes. So a zone would be Milsom Street or Bath Street, for example, and then there are chalets with numbers and names, and then each of the zones hosts the chalets. So you've got kind of three types of going on. You've got 2 types of label. You've got the zone and you've got the chalet, and you've got one relation type, which is links to. And then actually I've created a few labels. Through the presentation I created a selected label, and I created the shortest route to relationship to help kind of solve the problem.
These are just the labels.
Yes.
Differentiating zones and the chalets.
Yes, that's right. So if you want a query, for example, you wanted to say, give me all the chalets, then you would say match using the chalet label. So it's a way of distinguishing nodes, the labels are. They're kind of a bit analogous to tables in Oracle, except you can have multiple of them. Okay, yes, another question, yes.
Sorry, I'm a graph traversal nerd. So
okay, right, okay.
So I've got one question. I saw the word stream on
Stream,
some of the,
yes.
on some of the algo.
Yeah.
Does it actually, so when you're enumerating paths, does it enumerate one at a time and then filter on two, or does it enumerate all of them and then filter for the highest across the whole set? Does it accumulate all of them?
It does. It is accumulating it all. It is accumulating it all and solving the problem. I think I'm not 100% sure. I've got a feeling because there are two different. Sorry, the question was about the stream command, and so I think I'm not 100% sure, but I think stream's being used because it wants to return data to be continued in the cipher. It's going to stream the data back to the cipher query, whereas no stream kind of doesn't. I'm not 100% sure on that though. I'm not 100% sure. So yeah.
I've got one. Sorry.
Okay. One more. Yes.
So you're really experienced Oracle guy.
Quite experienced Oracle. Yes. Yeah.
Some of those queries look quite big.
Yes.
Especially the last one.
Yeah.
It looks hugely impressive. How would you compare sort of in terms of debugging and in terms of being able to reason about queries between this and PLSQL or some of the Oracle queries, standard query type stuff?
Yeah. So the question was about the difference between Oracle queries and Cipher queries and how easy it is to reason between them. So I think it's easier with the Cipher. I would say with that last query, that last query is about it was creating a lot of it was doing a lot of kind of stuff that you wouldn't use in reality. You wouldn't be creating these virtual nodes and virtual relationships. I used them because I wanted to make use of the tool to be able to display them to show a fancy picture at the end. I didn't, but in reality, I'm not sure how much they would get used kind of in a real application. But thinking about queries themselves, which obviously are used a lot in real applications, I think the difference is that when you're structuring your Cipher queries, you're talking in terms of paths. So it's actually very straightforward to reason. I want a path that goes from a zone to a node, and the way that it uses kind of ASCII syntax to do that, it's quite natural to do that. And with Oracle, you tend to find, certainly in kind of production environments, you'll see huge queries with joins left, right, and center. So the more joins and the more many-to-many stuff going on, actually, I would say it's easier to reason in Cipher than SQL. And I've seen pictures of, I think that's one of the kind of things that Neo4j will say. They'll show you a piece of marketing which says, look, this is an Oracle query, and it is exactly the same thing in Cipher, and it's kind of much more condensed. So I would say, certainly for when you've got systems which you've got lots of joins going on, complex queries that are using those kind of joins, that it will look nicer in Cipher. Yeah. Yes. One more question, yes.
Yeah, I have a question. So when your program runs, does everything stay in memory, or part of them is still on disk?
Yeah. Okay. So the question is about whether or not when you're running these queries, whether it runs in memory or whether it's on disk. So what Neo4j recommend is that they actually recommend that you've got enough memory to cover the database, so that it will load everything up into memory and run it. So therefore it will run in memory, but you need enough memory to be able to bring it in. And I think there's some trade-offs there. It's different. It's because of the way it is. Unlike Oracle, it's kind of more difficult to segment the data because everything's connected to each other. So how do you segment it in a way where you're only bringing up a certain, the kind of data that you want? So their recommendation, which is a easy recommendation to make, is to say, okay, well, let's have everything in memory. That's the recommendation. I think they've got some stuff which they're doing to how do you deal where you don't want it in memory, but the current recommendation is load it all in memory and then everything runs in memory. Yeah. Okay, that's it then. Thank you. Okay.